Greetings. Welcome to the second presentation of week 3 on wood products. This presentation, I obtained it directly from the textbook manufacturer, so it's not my original work. It comes with our Allen textbook, so it covers a lot of good information. It's a good presentation. We're going to review trees and lumber. We already did that in my last presentation, so I'm going to move quickly through those parts as there is a lot to cover. And then we're going to start to look more carefully at wood products, manufactured wood products as well, and then we're going to touch on some issues with heavy timber, fire resistance, and longer spans. And next week we'll be delving much more deeply into heavy timber construction, which is definitely one of my favorites. So I'm going to move along pretty quickly through these first two parts, and then we'll be looking at wood products. Alright, so beginning with trees. So again, a quick review of the makeup of a tree and how that skin grows on the outside. This is a diagram just pointing out that the bark is here on the outside and moving us through, and we talked about the hardwood and the softwood. Here are some nice images of softwood. So these are the cone-bearing, or not the deciduous trees. These are the firs and the pines. And it says it has a relatively simple cell structure, and the figure, generally speaking, plain figure. So the word figure, that's an important one. So that's the pattern of grain and surface features. So anybody who's working with finished wood, a finished carpenter, a cabinet maker, would talk about the wood's figure. And that's what we see here. Very kind of soft, pretty pine and fir figures. And hardwoods, so these are a little more pronounced now. The broadleaf deciduous trees, more complex cell structure, so a more interesting figure. So at the top we're looking at walnut, and the bottom red oak, and these are the pores moving in this direction, and here are the rays coming out in that direction. So again, if you're looking for a more expressive finished wood, you would look at hardwoods. Certified wood, so this is an issue dealing with sustainability, and there are third-party organizations that certify that the wood came from properly managed forests and was harvested properly, and it's very expensive to get certified wood, essentially. To pay this, wood manufacturers have to pay these third parties quite a bit of money to come in and audit and study and say, yes, in fact, we've traced this wood all the way back to the source, and we could certify that these folks are in fact producing this high quality wood. So it's expensive, and in pursuing LEED, it's an important piece of the puzzle, I would say. So sustainable forestry management, and yeah, that's essentially what we're discussing. And here, so this image, so this was coming from, let's see, where are we on the date here? Here, on the sources from the 08, yes, 08, so the map is from around that time. And then I jumped on the internet and I found an updated version of this, and this one is dated down here 2016. So going back to the time of this edition of the book, what we're looking at here in North America, essentially, that here's the Forest Stewardship Council, the certifying organization that is recognized by LEED at that time. So this is how much certified wood, the percentage of overall wood that's produced in America, how much of it is in fact certified. So here, at about 10 years ago now, we saw that 31% of North American wood. So that's relatively respectable. South America, less so at 10%. Europe, a very impressive 52%. And then Africa, Asia, and Oceania, all very little, 3% and below. If we jump forward, we see that North America is at 36 now, 10 years later. So this is close to current. So we went from 31% to 36%. So that's respectable. South America is at 6.8. So they actually dropped quite a bit, unfortunately, from 10 and change down to 6.8%. Europe as well dropped, 47%, originally 52%, and the others, Asia has made some increases up to 4.3%, coming from 1.9%. So kind of interesting. So I think North America is doing a respectful job in that regard. Okay, moving on to lumber. All right, so this image we saw in my presentation, we talked about the difference between the plain sawn and the quarter sawn. This is the nice, the annual growth rings are coming in at 90 degrees, providing us with the premium, very stable lumber, as opposed to plain sawn, where it's tangential and prone to cupping and prone to warping much more. So again, here's the plain saw. This is the more common broader grain pattern on wide face, distorts more during drying, uneven surface erosion and wear, and this is less costly. So this is the less stable. This is the look of it. Also called flat sawn and flat grain. And here's the quarter sawn. So less distortion during drying, much more stable, and more expensive, and just a better product, a better finished piece. All right, seasoning. We didn't talk about this, so we should. This is we talked about it in some regard about the drying. We didn't get too much into detail about how it was done. So after the lumber is sawn, then it's seasoned. It's dried. We talked about some of the defects, either in air or in a kiln. Seasoned lumber is lighter, stronger, and stiffer than green, unseasoned, and decay-causing fungus cannot survive in wood that has a moisture content below 20%. So these are some of the benefits of seasoning and drying properly. And we discussed the moisture content. So wood dries below approximately 30%, shrinks. We discussed that, and we discussed the directions. So I'm going to move on from that. This is another diagram of some of the they're calling drying distortions or defects. So this is pretty good. The ones on my presentation might not have been as clear. So we have cupping there on the face. A crook is, the face remains in plane, but it's bending in this direction. Again, I referred to the crooks when they frame walls. All the crooks are pointed in the same direction so as not to create stress on the drywall that follows. Bowing is the face is not in one plane. It's been distorted in that direction. Twisting is multiple bows. And here are some images of knots. This is not very clear at all, this checking and splitting. Splitting runs through and checking not, so that particular part's not too clear to me. Okay, seasoning. So continuing on with that, so we did talk about equilibrium moisture content and the importance of that. Here it's pointing out that for exterior products, that moisture content level could be at 15 to 19%, where if it's going to be for wood that's used on an interior finished product, it should be between 5 and 11%, quite a bit less. And we looked at the chart of all the various U.S. states and where they fell. So this is just a simplified graph of average moisture content. Okay, now on to surfacing. So finishing lumber. So it could be finished on one side or four sides, essentially, and that's what we see up here. So this is S4S is surfaced on 4 sides. Here's a product that was finished only on 3. So surfaced to make it smooth and more dimensionally precise, very important. Framing lumber usually done on all 4 sides, so this is surface 4 sides. Finished lumber could be 4 sides or 2 sides. Then there's also surfacing that happens after the drying, and then it removes the drying distortions. So this is surfacing after the drying, and this is before the seasoning actually occurs, before the drying. So this is sometimes more economical, best for wood species that don't distort too much when they dry. So there's some distortion that happens to wood when it dries out, and if this surfacing happens after that seasoning or drying, then that surfacing has the opportunity to remove any distortions that did occur. And then construction planking is just completely unsurfaced. That's what we see here at the bottom right. All right, structural grading. We did talk about this a fair amount. We're not going to get too deep into these charts, so I'm really not going to read all of that to you, nor send you on a quiz or a test out to look too deep into charts. I think we have more important information to cover than delving too deep. But here are the primary ones that we've discussed and that are most common to see: the select structural, number 1, number 2, and number 3. Here's a visual up here of what they look like. Okay. All right, and then that's structural applications, and then there's also appearance. So how they look regarding defects in terms of knots. So this is more just how they look, not so much structural issues. All right, structural properties of wood. So wood has both useful tensile and compressive strength, and that's true and important. Both wood and steel have relatively equal amounts of compressive and tensile strength, and the beams, well, first, let's just say a column expresses compression, two forces. Something's pressing down from above, and the column, the ground below, presses back up, so that's the compression. Tension would be a rope, something being pulled in two directions. And beams, very important, experience both. They experience compression on their top face and tension on their bottom face. And my point, what I was starting with, is that wood and steel both have relatively equal amounts of compression and tension, making them very suitable for beams. A lot of materials are not. Obviously, things like cable and rope have absolutely no compressive strength, and materials like masonry and concrete have very, very little tensile strength. So wood and steel have some of both, a nice amount of both, and could therefore be used as beams. This all varies in relation to the direction of the grain and how it's used, the presence of other defects such as knots. Strength load. So also varies with the duration of the load, how for what time frame a particular structural element is loaded. Moisture content we talked about. We're going to talk about some chemical treatments. All right, going to keep moving on. All right, dimensions. So just important to know, when it comes to dimensional lumber, as we call it, there's a nominal size and an actual size. So a 2x4 before it's surfaced is actually 2x4, but then after it's been surfaced, it comes out at 1.5 by 3.5. So 2x4 is the nominal size, 1.5 by 3.5 is the actual size. And all this pertains to all dimensional lumber. And then down here it points out that lumber is sold by the board foot, not at the Home Depot or Lowe's. It's not there. It's sold by the piece. But if you're buying a lot of lumber, building homes, then you would have to know how to buy lumber by the board foot. And essentially up here, a small diagram here says that a 1-inch thick board that is 12 inches by 12 inches equals 1 board foot. And that can be done in any configuration, but that's the math. The width times the length times the thickness divided by 12, and you get the board foot, and this is 1. So then here, if we're building something else, we have different dimensions to plug in. We still divide it by 12, and we still come up with the board feet. And that's, that's depicted down here. An example. Okay, moving on to wood products. So, manufactured wood products. Solid wood and wood fiber materials can be used in the manufacture of various wood products. So solid wood is the dimensional wood, the dimensional lumber that I'm talking about or referring to. Wood fiber is made up of smaller pieces, essentially, of wood, and we'll see some examples of those. And then these two components could be found in what is called a manufactured wood product. So manufactured wood products, there's a lot of variety in sizes and shapes. It's easier to produce them or producing them the way they are provides the opportunity to avoid defects. Those pieces would be eliminated. Produces more consistent quality than just standard wood. More efficient use of wood materials, less waste, yes. And then in some cases stronger, stiffer than solid wood members. So they're engineered essentially. All right, so here are some examples. So here's a glue laminated wood beam right here. So it's kind of built up. Laminated means that the pieces are adhered together, and we see horizontal plies. I would refer to them as plies just like plywood. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9 plies. That's how I would describe it. Beams are made from glued, solid lumber pieces. That's what we're looking at. Available, so they could be built to size, stronger, stiffer than solid wood. They can be curved. And what do we say here? Uses high-grade pieces very efficiently, only in the parts of the beam and with high stress levels, while using lower grade materials in other areas. So this is a very important point. I just had to read it to myself once. But it's basically saying, as I was just referring to, how a beam experiences compression and tension. It experiences compression up at its top face, and tension is greatest at its bottom face. And then when we move to the middle of the beam, the compression and the tension becomes nil, zero. It meets at the neutral axis, and there is none. So this is all to say that the upper face is experiencing the highest compression stresses, and the lower face is experiencing the highest tensile stresses. So therefore, this fourth bullet is pointing out that the highest quality wood could be used here at the bottom to resist the tension. The highest quality could be used here at the top for resisting those compressive stresses. And then here in the middle, where the stresses die back, then they could use a not as high grade quality piece. So that's efficiency. All right, moving on to structural composite lumber. So laminated strand lumber. This is oriented strand lumber. Glue shredded strips on the top right. So here we are. Okay. Laminated strand lumber or oriented strand lumber. So two different names for what we're seeing here. So these are essentially scraps like wood chips that have been glued together. So gluing shredded lumber together. So very, very efficient in that it is not very, it's not wasteful. It's very little materials wasted in this process. Laminated veneer lumber. So glued full depth veneers. So the bottom shown resting on its side. So that's here. So this is full depth veneers. So this is the veneer running in this direction. I think, if I could just spin this, I think the beam would be placed like this. This would be where the beam would bear, and then where it says full depth veneers, the veneer runs all the way from the top face to the bottom in this direction. So it was lying on its side there. So its depth is here. Just because it's lying on its side, I'm pointing that out. This would not be the depth. The beam would be taller than it is wide. And then parallel strand lumber, glued veneer strips, top left, so that's here. This I don't believe I've ever actually seen this in person installed. So in general, these pieces used for beams, headers, short beams over openings, which are short beams, studs, and I can't say that I've ever seen them installed as studs for that matter either. Perhaps a post or a small column, or columns, yes, and non-structural rim boards. So I've seen it in all applications except studs, I would say. Okay, moving on, wood plastic composites. All right, so made from a mix of wood fibers and plastics, maybe pre-finished, a good product for exterior decking and wood trim. So in new construction, you're going to be hard pressed to find anyone who wants to sign up for painting and staining natural wood outside. There's less and less and less of it. And having a house that's over 100 years old and having to maintain it, I understand why. While I'm a purist about wood and what I like, I wouldn't want to sign up for that type of the maintenance required. If I was building something new, I would definitely steer away from that, and that's where these pieces, I think, have a very legit and understandable life. So, less stiff, greater thermal expansion and contraction than solid lumber, so I think greater thermal expansion and contraction probably means that it moves less, actually. That's how I would read that. Also, plastic lumber, greater than 50% plastic, has both finish and structural applications. So, I think exterior decking and exterior trims on structures, on buildings, would probably be where you'd find this most often, and understandably so. All right, structural wood panels. So this is we're looking at sheet material here. So sheet goods. This would be your floors or your wall sheathing on the outside of a frame, and we'll look more closely at that next week. So plywood has laminate veneers. That's this I can't tell exactly from this photo, but the top and the bottom both kind of look like plywood to me. And then composite panels, face veneers bonded to a solid core. So again, the veneers or the plies are the pieces that make this up. So plywood would often have 5 or 7 perhaps plies, and then the face veneers are the ones that are on the outside. So the solid core could be the structural part, and then something that would otherwise be very expensive, a nice wood, could be used as just a thin veneer. And so this would be used for cost savings and for finished materials inside. OSB, oriented strand board, very popular and inexpensive for sheathing. We'll look at sheathing next week again. So here, shredded strands. That's what we see there. And then particle and fiber boards are not pictured here, and they're made up of smaller pieces yet. So very efficient in that they don't waste a lot, but they have their limits in terms of what they could be used for. Okay, so standard sizes for these sheet goods. So standard panel sizes 4x8 is the size of the actual sheet, and thicknesses range from as little as 5/16 or a quarter, or actually less than that, quarter inch, up to inch plus. They can be very thick. Used as sheathing, so this is the outside of our rough framed buildings, and as subflooring. Span ratings, everything is given, so the thickness is given is accounted for when determining how far between rafters a material like this could span. So should the rafters or the floor joists be at 16 inches on center, or would they be on 24 inches on center? So the structural engineer or the architect would provide all of this information essentially. So if the span is X, then we need a thickness that is Y, for instance. And then there are some durability classifications. So where's this being used? Is it exterior application, or is it here exposure 1 or exposure 2? So which just reflect the amount of exposure or the time that the exposure will be occurring for. Okay, moving on. So we did talk a fair amount about grading. I'm not going to dig into this too deep, and I'm not going to expect you to, but suffice to say that everything that we've been discussing, exposure ratings, sizes, the applications, it's all found on the stamp essentially, and that information's on each piece of wood. So I'm just going to move on. We're not going to dig into these too deeply. Okay, wood chemical treatment. So 2 different reasons to treat different timbers. So fire retardant treated wood. So chemical salts or pressure impregnated into the wood to reduce its combustibility. So this is used where building codes restrict the use of combustible materials. It's not very common to come across fire retardant treated wood. In general, it has its places. Maybe I've seen it as kind of where backing was needed for nailing things, maybe in what would otherwise be a commercial application. But typically, it's going to be all. If the easiest way to follow code would be to have everything steel, studs, and concrete, and just avoid wood altogether. But where some wood would need to be incorporated. Again, maybe for blocking, for mounting finished pieces on the interior. That's times I've seen it. But often there's not a lot of wood being put into the structure of a building. If it's just easier to go with steel and concrete, I would say. However, preservative treated wood or pressure treated wood, much more popular. So this is any wood that's exposed to weather, in contact with the ground, or high termite risk. Or in contact with concrete would be pressure treated. Okay, so this is getting into the finer points of preservatives, and we are going to skip over that. All right, and now on to manufactured wood products. All right, so different structural members essentially. So trusses are, especially as our next chapters will be on residential or low-rise framing. Trusses play a very big, important role today. So they are typically made up of 2x4s or 2x6s, and then they have toothed plates or gusset plates. That's what's pictured right here. The whole truss is laid out on a jig, and then the gusset plates are placed where they're supposed to, and hydraulic presses quickly put them together. They have very long span capabilities, more so than probably any other structural member, because they're triangulated, so they're super stiff, and they do not use a lot of material, so they're very efficient. And in low-rise construction, typically they're put up very quickly, very easily with small cranes. This points out that they do complicate attic spaces. They do have some trusses that are designed with open areas in the center, so that there would not be any diagonals there, but they're not as easy to work with in that regard as just a traditional framed attic space could produce. Okay, moving on to I-joists, also very efficient. So can span further than solid lumber, uses less raw materials, so the top and the bottom flanges are solid lumber or composite. So here's a top flange, this piece right here. Here's our bottom flange, and this is the web of the truss. Here, so top and bottom flanges are solid wood or a composite. LVL is shown here, so that's again the laminated veneer lumber, and that's what we see right there. Those are the laminates. And then the web of OSB or plywood, so this is the web, and again that is the OSB, oriented strand board, made up of the shavings. So a very, very efficient and popular choice for joists, for residential and low-rise joists. One thing they don't have going for them is that you cannot run mechanicals through them. Some do have punch-outs, but in general they never get altered when they get to the job site, and you would have to follow the punch-outs that are provided if you were attempting to run duct or pipe through them. Trusses are much more easy to accommodate such mechanicals, obviously. All right, factory-built housing. So there are two different types here. We have our manufactured mobile homes. So these are just built to a broader nationwide standard U.S. HUD. And then modular construction is different. So this is built to local building codes, actually. So this is where pieces like this would be brought in, perhaps two of them, and they would be placed together and joined on the site. So again, seemingly similar to a mobile home, but it is actually finished on the job site, and it is built to local codes. So it's of equal, it lives up to the same code restrictions that site-built homes do. Okay, moving on to timber framing.